There we go. Okay, welcome to our 29th lecture in the course. We're going to continue talking about coronal lines now for a little bit. And before we go on, I want to actually make a little remark about something else. I was just attending an NSO talk earlier today, and I was, as far as I remember, the only person with the camera on. So I was really wondering how was the lecturer feeling during that time. And actually, I just want to use this opportunity to thank all of you who are keeping their camera on during these lectures, because it really allows me to like feel that we are really doing something together, even though I'm doing most of the talking. And of course, I will never force you to keep your camera on, and you do deserve to do, for example, knitting if you want while you are listening to the lecture, or washing your dishes, or whatever you want. But anyway, I just wanted to thank the ones who are keeping their camera on, and to say that I really appreciate it, and it actually helps me feel included in the talk. Anyway, today we're going to be talking a little bit about scattering and the coronal lines formed by scattering, and we're going to be talking about forbidden lines a little bit. Actually, there will only be a really little bit about the forbidden lines in the end, so they maybe don't deserve it here, but I feel like forbidden lines are an important thing in astrophysics, so yeah, we should at least mention them. And we will go back talking about some of the scattering concepts again, and maybe we will actually revisit some of your homework problems, and so on and so on. So let's remind ourselves that when we started talking about the corona, we moved to completely different physical regimes, and we had some simplified radiative transfer, mostly in the term of just that solution of the radiative transfer equation became much more simple. We were just integrating along the line of sight, and that was it. There was no these complicated things like Eddington-Barbier relation and stuff like that, because everything is optically thin. And we saw in the previous class roughly what are the emission measure, which gives us a rough idea about how much of the material is doing the emission. And we also saw something about a differential emission measure, which in addition to amount of material also tells us how much material there is at various temperatures. And today we are actually going to be talking more about the physics included in the line formation than specifically about the coronal diagnostics and coronal physics, because as you know, first, corona is not my field. Second of all, I'm more of a spectral lines radiative transfer guy than the solar physics guy. So I'm always more interested and feel more comfortable talking about interesting effects that we see in spectra than what it really means for the sun and the solar physics. And I'm sure that you have much more opportunities to hear about that in your other classes and in the lectures that you're attending. So again, I took a lot of examples from some other people's lecture slides and talks. I found recently a very detailed review paper from Living Reviews in Solar Physics by Delzana and Mason. It's 250 pages, and there is a lot of technical things that might be super useful for you if you are actually doing solar coronal diagnostics, because they really visit all specific spectral lines or specific classes, describe a lot of physics, give a lot of useful graphs, and so on. It looks like a great paper. Of course, I didn't read it fully, but I took some examples and read some of the theoretical explanation. Then I again took some ideas and even plots from the slides made by Stephen Kramer and his lectures in 2016. Then I randomly found some lectures by Alexander Kosovichev from Stanford, took some of his ideas. And finally, I also drew some inspiration from the last year's lectures by Alim Paraskhiv, who briefly told us something about the coronal inversions. And there is probably much more topics. And actually next class, when we discuss about how everything went and so on, I'm going to list all the things that we didn't cover here, so that you know where, and maybe give you some resources to look forward and read forward if you want to. So we said that corona is special because it's hot and it's the densities are very low, and we said that a lot of things will change there because we have really a lot of ionization, low opacities, high thermal broadening, but also some exotic effects can appear. And you usually see this plot here and you say, oh, wow, well, corona is that layer where temperature rises very quickly or the density drops very quickly. But how does it actually look like? And then I can give you my goofy answer, which is, well, it depends on the wavelength, as everything else in the sun, except here, contrary to the chromosphere and photosphere, so in photosphere and chromosphere, by looking at different wavelengths, we are looking at different depths, which are naturally, because of the structure, which is highly stratified, we are looking at different temperatures, velocities, and magnetic fields, right? And that was the main premise of our homework 1, problem 3, and homework 2, problem 2, where we were saying, well, different wavelengths correspond to different physical conditions, and we were mostly talking about the temperature, which in photosphere means the source function, right? In the chromosphere, because there is no stratification and things are listening much more to the magnetic field than they are to the gravity, we are seeing actually different densities and different temperatures, which are where they are, right? And we are not talking about the contribution function to the height, we are talking about the contribution function to the temperature. And that allowed us to understand a little bit why people ascribe to different AIA channels different temperatures. And you might be confused because there are these are images. There are no spectral lines here, but spectral lines are here. This is the light which is dominated by the spectral line emission, right? We look at the image. We integrate spectral line emission over, or multiple spectral line emissions over a wavelength range, but what we see here is dominated by the spectral line processing. So yeah, sure, you won't be able to see how broad your line is. You won't be able to see how much your spectral line shifts to the left or to the right if you're just looking at the image. But if the image is in a filter that is dominated by a spectral line, you are still seeing the contribution of the spectral line emission. And we said that for most of these channels, it is dominated by this electron density squared term times the contribution function to the temperature, and that by looking at different wavelengths, you can basically decipher different temperatures by analyzing their emission measures and differential emission measures. And just for the completeness, there are also these first 3 images here, which are the images from HMI. HMI is another instrument than SDO, which is basically measuring continuum intensity in the optical light, is measuring line of sight magnetic fields and line of sight velocities, so that we have some idea about what is going on. And this is actually super beautiful. This image here tells you a lot about the sun on its own. And a lot can be learned from these images, even though sometimes we spectroscopists, we like to think that this is not enough, but actually there is a lot of cool physics happening here. So let's just very quickly remind ourselves what was our analytical approach here. Well, we imagined that, and actually it turned out that it doesn't matter whether we are above the limb or on the disk. We are always in the some optically thin regime, because even when we are on the disk, underlying radiation is very weak. So it's basically only corona that is contributing here, right? And I said that in principle, we can always find intensity by just integrating. So we focus on a wavelength, we find emissivity on that specific wavelength everywhere along the line of sight, and we integrate it. Now, keep in mind that this emissivity can vary wildly. Why can it vary wildly? Well, for example, because the density can vary by many orders of magnitude between these different blobs here, or velocity can vary, so the things will change, right? The maximum of emission, and thus the wings of the line and the continuum in the center of the line will move left and right, and you are still focusing only on one wavelength and integrating emissivity at that specific wavelength along the direction. And then I said that usually, whichever line we are considering, we are going to try and find this term here, which is the emissivity. And this is one of the first things that we did in our course, which was to basically justify that this really is the expression for emissivity. And it makes sense, right? There is a bunch of constant, hc over 4 pi lambda. There is the population of the upper level, which basically says, well, the more particles I have that are excited, the more emission I'm going to have. I have this specific constant called Einstein coefficient of spontaneous emission, which tells me basically how efficient my atoms are in the emission processes. Higher this constant is, more often emission happens, more larger the emission coefficient is for me. And finally, I have this important function here called phi lambda, which determines how my emission is distributed over the various wavelengths. And we know that this is where all the line broadening mechanisms and line damping mechanisms come into play. A small, brief question for you to see if we agree and if we are still thinking about the same physical regimes. For the corona, what do you think will be more important? A line broadening, which means Doppler effect, or line damping, which means everything else? Any opinions on that? We will need line broadening today a little bit to explain something. So temperatures in the coronas are huge, densities are low. What do you think will be more important? Thermal line broadening or collisional line damping? Yes, Brian, I agree with Brian. Brian said Doppler effect, which means random Doppler effect due to the random thermal motions, and I would agree. So I would say that in the most cases in corona, simply due to these huge temperatures, there is a lot of random broadening, and the lines are generally going to be super broad. And actually, I'm going to tell you today about a very, very interesting physical effect that will allow us to learn something new about the line broadening. Okay, very good. So let's remember where we started from. And we said that one of the assumptions that is always more or less reasonable to make, sometimes it's not, but its alternative is just so complicated that you can't go there. It is very often reasonable to assume the so-called statistical equilibrium, which presumes that your plasma is in some sort of steady state, which means that your level populations are not changing, which in turn means that the number of processes which are populating the levels and depopulating levels is the same. And I wrote to you last time this equation, which says basically, well, my upward processes from one level are the absorption, which is the first term, plus collisional excitation, which is the second term. They have to be equal to the number of processes coming down from the upper level to the lower level, which are spontaneous emission, which is the first term, stimulated emission, which is the second term, and collisional de-excitation, which is the third term. Now, note that I'm presuming here something called two-level atom model, where no other levels, no other processes are even considered here. There is no photoionization, there is no collisional ionization, there is nothing. We somehow presume that we already dealt with all these processes, and now we are only looking at what is happening between these two. And another thing that I want you to remember is that best collisional partners, as I like to call them, are electrons, which means that electrons are responsible for the values of these CLU and CUL that you see here, and that the electron number density is basically hiding in these things here. And at some point, we will unhide it, as we did in the last class when we were finding these n electron squared dependency for the collisional lines, right? So once again, we assumed that in the de-excitation process, collisions are not important, stimulated emission is not important, and that only spontaneous emission is important. And then our equation simplified to this, right? And basically this, coincidentally, is our expression. This goes into our expression for emission, right? And what I did in the last class, I said, well, you know what? Some lines, especially the ones formed closer to the surface of the sun, are collisionally dominated, which means that main culprit for the excitation is this NL times CLU term. And then I unpacked further CLU, NE appeared there, another NE appeared from NL, and I get this famous NE squared dependency. And then we were discussing about it a little bit, and I said, well, the square dependency can be understood like this. Since collisions are responsible for my excitation, which is after that responsible for my emission, I have one NE dependence, because more electrons there are, more material overall there is, and thus more particles that are in principle capable of emitting there are. But also more electrons I have, more collisions I have, so more of these particles are going to be excited. So I have NE squared dependency there. However, and one of the examples that I used for this was 171 AIA line, for which you can see clearly from the pink and the teal lines that collisions dominate the radiative processes. Of course, what we have here is that these are the downward processes, but I assure you that this is also true for the upward processes, for the collisional excitation and the radiative excitation here. Okay, cool. Well, what, however, would happen if I went so far away from the sun that this CLU dropped down so much that actually my radiative excitation was not negligible anymore? Well, let's see what would happen in that case. Well, in that case, I could forget about the collisional excitation, and I would see that actually my population of my upper level, in that case, depends on the population of my lower level times the Einstein coefficient for absorption, which is just some constant, times the mean intensity of the radiation. So don't think about the second line yet. I mean, I should have actually hidden it. Let's just think about this one first. What this basically tells me is, if I presume that my lower level population somehow is very closely related to the total number of the ions that I'm considering, which actually for resonant lines really makes sense, because we know that for resonant lines are the lines where the lower level is the ground level, and we know that no matter how high the temperature is, most of the electrons are going to be in the ground level. So what we have so far is that the population of the upper level is proportional to the total number of particles, which makes sense. If I have more particles overall, I will have more excited particles, but is also proportional to the mean intensity of the radiation field. How do you understand this second statement? How would you explain this to yourself? The number of excited particles depends on the mean intensity of the incoming radiation field. Does that make sense? And if it does, could you tell me how you understand that? What is your interpretation for this? Or if it doesn't make sense, you can just type minus or say it doesn't make sense. Or if you think it's too easy and I'm trying to trick you, don't worry. I'm not trying to trick you. I would like to hear your interpretation. And if you don't want to say it, you can type it and I will read it happily. We can think for a while. I don't want to stress you. Let's take 1 minute.
Ivan, could you repeat the question? Michael?
Yeah, so the question is, this first equation tells us that the upper level population is proportional to the mean intensity of the incoming radiation. Does that make sense? And if it does, why? This is not super new for us. We already talked about this a little while back, but we are revisiting it in the context of coronal lines. We are in a different physical regime than we were before. We started from here. Last class, we neglected radiational excitation. Now we neglected collisional excitation. And we got this, the first line here. How do you interpret that?
So if the only mechanism that can populate the upper levels is the incoming intensity, then you would expect that population to be proportional to the incoming intensity.
I absolutely agree. I absolutely agree. So if only mechanism that excites my my levels is absorption of the light, So not collisions with other particles, but absorption of the light. I expect that more incoming light I have, which is determined by this capital J here, more excited particles I have. That's a reasonable assumption, I would say. And let's see if other people agree. Does it make sense? Okay, it seems that it makes sense. Cool. So then I can do the same dirty trick that I did last time. Instead of using Nu, AUL in my equation for the emissivity, I can plug in the left-hand side instead. What I'm going to get there is that my emissivity is now proportional to the lower population of the lower level, which is also proportional to the total number of particles, times bunch of constants, times the mean radiation field. This is very interesting now. I now got that my emissivity doesn't depend anymore only on the thermodynamic properties of the gas, but depends on the thermodynamic, which are hiding in this NL, and on the radiation field itself. Now, can anybody guess what next step I could take this to get even more simpler equation? I could divide both sides with something. Does anybody have an idea with what? With opacity. Very good, Jonathan. So this term here is actually very similar to our expression for an opacity, this circle term here. And I'm going to go to the next slide because we have it written out there. This left term, neglecting stimulated emission, even though I didn't have to neglect it, I could have carried it here. The equation just would look a little bit more ugly. I can write this first term as the opacity, divide both terms with opacity. On the right-hand side, I would have the mean intensity. On the left-hand side, I would have the source function. And I would get something that we are actually familiar with. That, of course, neglecting polarization and all the fancy effects, in the case of pure scattering, source function is identical to the mean intensity. It doesn't depend on anything else except on the mean intensity. It doesn't depend on the temperature. It doesn't depend on the it shouldn't depend on the density anyway, and so on and so on. Very, very interesting, right? So it is also very interesting to see that in Corona we had some distinction between the collisional and radiative and the scattering lines, but okay, we can discuss that further. And this actually somehow makes sense, right? Because the amount of emitted photons, which is what we have on the left, regardless whether we want to think about it in terms of emission coefficient or the source function, has to be proportional to the number of the photons that are arriving to that point, right? Okay, well, let's then just test ourselves with a very, very quick question that I already asked you. In which of these two cases will the scattering emissivity be higher? This is also related to your homework problem number 2 that you're currently having. I'm giving you 1 minute. Let's go now. I can show you once again. Slides. Then the problem. In this problem, let's say intensity of the red lines is the same. It's just that in the red side, the red lines are coming from more directions, or larger solid angle, if you prefer. Red lines is the incoming radiation. Green lines are outgoing radiation, which is actually fairly weak. I didn't emphasize it here. So what do you think? In which case will the scattering emissivity be higher? And we are looking from above in this case. Usually we look from the side and the illumination is from below, but here I changed it. This is an old slide where we still didn't know what the prominence is, or coronal loop, or coronal hole. So what are the answers, left or right? Exactly, Jonathan. Exactly, Michael. Exactly, Megan. Yeah, when we integrate to find the J is the same as in your homework problem. In this problem, I'm integrating, technically, in both cases, I should be integrating over 4 pi. But for right-hand side, I have roughly, what is it? 1/3 of the solid angle is something, 2/3 is nothing. Left case, almost everything is nothing. So I'm simply gonna get larger mean intensity on the right-hand side and thus larger emissivity. Okay, cool. Well, here are some reminders for you to remind you about the things that in general, this thing can get much more complicated. And I know that that this is a little bit iffy, and the general case is much more iffy. General case is the non-LTE transfer in the spectral lines, and we always should remember that our emission and absorption coefficients follow from the level populations, which in turn follow from the statistical equilibrium equation. Then, if we simplify this statistical equilibrium equation that in principle should be written for all the relevant levels inside of the atoms, and if we say, well, I don't really want to treat all the levels, I only want these two ones where my spectral line is formed, I can then just say, well, source function is just a combination between thermal contribution, which is this famous B, and scattering contribution, which is what we have been talking about now. And there was this, you know, a fractional term which was determining contribution of these two, which was called epsilon, right? And then we said, well, if we are really, really high in the atmosphere and there is really a lot of scattering, I can basically assume that this epsilon is 0, and then there are no thermal contributions whatsoever. So I can presume that my source function is basically equal to the mean intensity. And then in the most of the cases, I can presume that in the corona, in the solar prominences, in the loops, in all these other objects, simply my opacity is so low that I can just integrate the emission coefficient along my line of sight and obtain intensity that way, right? And actually, this whole story, this whole logic that I was following here, that my emissivity is proportional to the incoming intensity and so on, technically, I should have been writing J lambda here, except that in spectral lines, it's not really J lambda, but for the continuum with J lambda. So we're gonna touch on some of these aspects here, but dimensionally, this still makes sense. So don't worry. Anyway, what were we talking about? Yeah, we were talking about the fact that this scattering is not super new to us, and that we actually started studying it from some continuum scattering cases. And actually, corona is the place for scattering, because we have all different kinds of scattering there, not only in the spectral lines but also in the continuum. And actually, now I want to talk to you about first of all some very simple diagnostics that we can make by looking at the scattered light, but also about some very interesting and very, for me, subtle and nice effects that are happening when we have scattering of radiation, not only in spectral lines, but also in the continuum. So you know that there are all these famous, letters for corona, and I never really learned all of these, but now I at least feel confident about K, F, and E corona. But apparently there are a few more letters. So today we're going to be talking a little bit about the K corona and F corona. So K corona, apparently it's called K corona because K is for continuum, but in German, so it's K, not C. It is the light that we see and is created by the scattering of the photospheric light on the free electrons in the corona, and this is something that you typically see during the eclipse. So this is one of the beautiful images from the eclipse. This maybe was made from Turkey in 2006, and I'm actually very happy to say that I was there. I didn't make this photo, but I also have some which are not that bad. Anyway, how do you think in that case? I'm just gonna ask you now what your hunch is telling you, then I'm gonna tell you the answer, and we're gonna do some calculations afterward. I'm looking here and I'm telling you that all the light that you see is coming from the scattering on the free electrons. So there is no spectral line now. There is only photons, like little balls, hitting electrons, which are little bigger balls, and scattering of them and changing direction. How do you think the brightness here relates to the electron densities? When I say how, I mean, is it quadratically? Is it linearly? Is it square root? Some other, law? What does your hunch tell you? And I'm going to give you 2 minutes. Sage says linearly. Do we have other opinions? Okay, I'm going to give you a minute and a half because I'm slow with this. So think about it in this way. The intensity that I'm seeing depends on the thickness, and thickness is pretty much the same for the image. I'm integrating along the whole corona, and it depends on the emission coefficient. Marcel says quadratic. Okay. Other opinions? So we have one linear, one quadratic. Emission coefficient, on the other hand, is opacity times, for scattering, mean intensity. That is what we found here, right? We found it for a spectral line, but for electrons, it's exactly the same logic, right? Everything that I absorb is being scattered away. Two seconds. Okay, there are no other opinions. Any last chance, takers? Okay, Megan also says that it's quadratic. Well, I'm gonna say that it's actually linear, because this is a scattering regime. Why is it scattering? Why does scattering regime imply linearity? Well, one way to explain that is what I just said, is to say that, well, emissivity, my scattering emissivity needs to be proportional to two things. Amount of the absorption that I have, which is determined by my opacity here, times the amount of incoming radiation. Something similar to the line processes, just maybe generalized if you want to the continuum processes. And actually one of the ways to explain continuum scattering is by using virtual levels. You say, well, scattering happens by exciting my particle to a virtual level and then de-exciting, and then voila, I get scattering. So what does that mean? It means that I will write my opacity for this so-called Thomson scattering. It's the simplest opacity of all. It's just number density, times the Thomson scattering cross-section. So my emission coefficient is going to be equal to the electron number density, Thomson cross-section times the mean intensity. And then whatever I have will just basically be integral of this along the path. J and Thomson cross-section are going to come out. Well, J shouldn't really come out, because when I'm integrating this, I'm at different distances from the sun, and we were just discussing between the class how when we are at different distances from the sun, we see different J. But here I'm making some very, very rough approximations, and I'm going to see this integral of NE times ds, which is something that we call column density, which tells me how much particles I have along my line of sight. Cool. Well, let's use this to estimate the density of the K corona. Okay, so K corona is actually super faint, and there is really good reason why we only see it during the eclipses. It's because its intensity is 1/1,000,000th of the disk intensity. So you really need something to come in front of cover your disk so that you could see corona, because otherwise, you know, like this dynamic range of 10 to the 6 is very hard to capture. Okay, so I'm going to tell you the following things. I'm going to tell you that cross-section for Thomson scattering is 3.3 times 10 to the minus 5 centimeters squared. So this sigma here. Okay. And I'm going to tell you that, well, I'm not going to tell you anything else. I'm literally just going to give you this sigma and ask you to estimate electron densities. So you know the ratio between the solar, between the intensity of the corona and the solar disk intensity. You know the sigma, and let's try and estimate the number density. So if we go back, let's see where these things go, and I will let you think a little bit about this. We know that ratio between this intensity here, which is the intensity that we see, and this intensity here, that is the incoming intensity, is 10 to the minus 6. So there is some angular integration that produces this J here, but that angular integration can account for a factor of few. It can't account for many orders of magnitude. So I roughly know that my I lambda over J is 10 to the minus 6. I gave you sigma. Sigma is 3.3 times 10 to the minus 25 centimeters squared. How would you go on about finding electron density here? Let me give you 3 minutes. So try to sketch it. Try to see along which line we are integrating. Try to estimate what is the length of that line. Again, up to the order of magnitude. And let's try to figure out what electron density should be in that case. I'm going to get a bit more water. You're doing these topics a little bit in reverse, but since continuum scattering is more similar to line scattering than to collisional lines, then I lumped it like this. So once again, the logic is that I lambda over J is roughly 10 to the minus 6, because J is determined by the solar intensity, and we know that ratio of the observed intensity to solar intensity is 10 to the minus 6. And we are looking to find this last term, which is electron density. And for that, we need to assume roughly over, show sigma Thompson, of course, 3 times 3 times 10 to the minus, 3.3 times 10 to the minus 5 centimeters squared. Forget this text here. You can read it later and think about it. What happened with the time? Okay, 14 more seconds. Okay, the time is up. Anybody has a guess? Does anybody have a guess? Are we looking at the line along solar limb? Yes, Michael, roughly, somewhere above the solar limb. I mean, the disk is obstructed here, so we can't look anywhere else. We only need orders of magnitude. We don't need complicated. Megan says 10 to the 5, very good estimate. I would say I got a little bit larger than that, but it's totally in the good ballpark. Other estimates? Okay, how about this estimate? Along how, actually how to phrase this, what is the distance roughly over which I have to integrate my, my emissivity to get my intensity? Jonathan got 10 to the 7. I would say 10 to the 7 is a little bit closer, but let's answer this question. Along how long path am I integrating here? Order of magnitude. You don't even have to give me a number. You can just compare with something. Jonathan said 10 to the 10. Why 10 to the 10? Solar radius. I totally agree with that. Let's look at my solution. So when we are looking here from the right, we are looking at the radiation passing. You see, I drew corona blue now, just for, goofs. When we are integrating along this path here, I'm integrating over all this delta S here, right? And this delta S is order of solar radius. What is solar radius? Well, 696 times 10 to the 3 kilometers. So it's roughly, I could round this up to 1,000,000 kilometers, which is 10 to the 6, which then when I turn it to centimeters, would be 10 to 11 centimeters even, right? And then if I have these 10 to 11, these 10 to the minus 6, when I do the math, I will get something of the order of 10 to the 7, 10 to the 8, maybe even less, depending on what I took for this distance here, centimeters to minus 3. If you were to compare this to your first homework, you would see that these densities are many orders of magnitude lower. And in your first homework, I even didn't give you photosphere. I gave you something a little bit higher than the photosphere. If you use them, these constants. Well, very good. So basically, we can very roughly use the electron densities to infer the. We can very roughly use this electron scattering and looking at the K corona to diagnose electron densities, not only in the corona but also in the prominences. And actually, there are some very neat methods developed by Peter Heinzel and collaborators that allow us to diagnose prominence electron densities by combining wide light observations and spectral line observations. Well, but then you might have also heard about F corona. Okay, it is very similar, except instead of scattering on the electrons, we are scattering on dust particles. Believe it or not, even in these huge coronal temperatures, there are some dust particles that are living there, and they can scatter the light. And actually, scattering is, in the first approximation, behaves very similarly, except that when dust is scattering the particles, the angular redistribution and some other exotic things that we will talk about in a minute look a little bit different. And actually, this F corona extends very, very, very far away. And we sometimes see it even during the night as the so-called zodiacal light. And that's actually not anymore the corona. It's basically the interplanetary space. This is a very nice image that I took from the PhD thesis of this person here, which is called The Survey of Radial Velocities in the Zodiacal Dust Cloud. And actually, I'm wondering if anybody knows any other notable works by this author here. I'm going to open this question also for the more senior members of the audience. Yes, exactly. Shudong knows the answer. The author of this PhD thesis is the guitar player of famous band Queen, right? And it actually just turned out that when I Googled zodiacal light to find some nice images, this PhD thesis came out. And actually, here is another. Okay, we can move on back to our topic, but it was interesting to find out that person, after all these things, found time to do the PhD thesis. The corona actually extends depending on what brightness you want to define here as the corona, extends very, very far away. This F corona. And here you actually have a graph which shows you how the brightness of the corona changes with the distance. And it also has a few, checkpoints like desert sky brightness. And desert sky brightness is actually still very high in the units of solar disk brightness. Even, I'm presuming that the desert sky brightness means very, very clear and nice sky, not something that you would see from a big city. So even in the nice conditions, you can't see the corona, obviously. But obviously when you have the totality, when some natural occurrence blocks your disk, you have much better observing conditions. Your sky is much more clear of the scattering of the scattered light, and you can see corona up until, well, 3 solar radii. It sounds a little bit maybe unrealistic, but okay, why not? Yeah. By the way, always very interesting to think about. Oh, amazing call. 39 from the Night at the Opera is the best astrophysics related rock song out there. So everybody, you know what to play after the lecture is done. Anyway, what I wanted to say is that this is also a very good opportunity to remember how sensitive our eyes are, because they can see, you know, we won't really go blind if we look at the sun briefly, but even during the eclipse, we actually see, we can almost see the corona, or we can actually see the corona. Okay, anyway, let's go back to one very important difference that is related to our spectral line diagnostics and understanding some spectral line emission processes. Here are some spectra of the F corona and K corona observed by Serge Kuchmy recently. And what you can see here is something that is very, very, very interesting. So the red line is the superposition of the so-called E spectrum, which is emission line spectrum, which comes from the lowermost regions of the sun. K spectrum, which is the, as we have just talked about, electron scattering, and F corona spectrum, which is, as we just said, dust scattering. And the purple is basically the same, just with the removed F corona. Okay. You can see here, and the lowest thing is the solar spectrum, and this is a huge chunk of solar spectrum. 400 angstrom is a really nice and huge set there. And what you can see is that in the spectrum of which includes F corona, which includes scattering on the dust particles, you see the same absorption lines as you see in the photosphere. However, when you look at only K plus E spectrum, you don't see that. You see basically more or less flat line. How can this be? Let's first understand and decipher how can we see photospheric absorption lines in the spectrum that is caused by the dust, and then later understand why we don't see it in the spectrum that is caused by the electrons. I'm hiding something from you here, and that's why I'm using this very awkward phrasing, caused by the dust and caused by the electrons. So think a little bit about what is actually happening. And okay, Sage is already providing the answer. And tell me why I see photospheric spectral lines in the F corona. Sage says dust is reflecting. Do you care to elaborate? I'm pretty sure you know the answer and that the answer is correct, but so I'm going to ask you to elaborate a little bit.
Honestly, that's about the extent of my knowledge. Sorry.
Okay. Well, you are right. Okay. The thing is that dust, as well as the electrons, but we're going to see that there is something very, very subtle related to electrons, which leads to very interesting effect. When dust scatters the light, it basically does exactly what Sage said. It reflects the light in a way, which means if I illuminate it with the spectrum that has absorption line, it's just going to scatter the light, and each wavelength is going to be scattered exactly in the same way as it entered, and my reflected light is also going to contain the spectrum, right? Imagine how the telescope works. You are bouncing your incoming light through many mirrors, and then what you see in the end is basically the absorption spectrum of the sun, right? So dust does something similar. It reflects the sun. It reflects the incident photospheric radiation. The radiation comes to us, and we see the absorption spectrum, right? So the black line is the original solar spectrum. It determines my J. And my dust behaves, sorry, this shouldn't be electron density. This should be dust density here. So my emissivity of my dust is basically dust density times the cross section times the incoming radiation. And I see the same spectrum that came in. Does that make sense? In a way, dust is just redirecting the incident light. Does that make sense? Cool. What's the deal with the electrons? And I will provide you with some hints. It has something to do with the temperature of the electrons, and it has to do with their velocity, because the electrons are very light and the dust is very heavy. I'll give you 3 minutes to think about this. Why? What happens in the electron scattering process so that if we have electron scattering, we don't see the lines, but if we have dust scattering, we see the lines. So the electrons are also scattering, basically in the same fashion as the dust is scattering, except electrons are also moving really, really quickly and randomly, right? Because the temperature is the same, dust is heavy, electrons are light. And to understand this better, to maybe give you another hint, don't think about scattering as scattering. Think about it as the absorption followed by emission. Try to make an analogy with spectral line processes. Okay, 1 more minute. Or if you want more hints, just think about the emission process. When I have emitting material that's emitting only in one wavelength, but that emitting material has huge velocity dispersion, what will happen with the emission? Jonathan says electrons absorb kinetic energy and do not re-emit the photon. No, they scatter the photon. They definitely re-emit it. If they wouldn't re-emit the photon, I wouldn't have the purple line here. So they do. Yingji has one answer. Let's see what is this saying. The large thermal velocity of the electrons creates some kind of very broadened spectral PSF. Very interesting phrasing, which completely smoothens. I don't know how it should be deferred. The scattered spectra. I totally agree with this, and let's see what this actually means with the help of this ugly sketch that I created here. So let's say that we have this cloud of electrons here, and the electrons are moving very, very fast. Okay, and I'm pinpointing 3 electrons here. One is moving perpendicularly to us, one is moving toward us, one is moving away from us. And now I'm not gonna say, well, you know, each of these is scattering one photon. I'm gonna say each of these electrons is scattering a spectrum. Okay, the incoming spectrum is, let's say, one absorption line. The electron that is moving away from us is gonna scatter that spectrum, but the spectrum is going to be redshifted because the electron is moving away. So that's why I told you, try to imagine that it's absorption followed by the emission. The electron absorbs the whole spectrum and then emits it, but it emits it in a shifted manner toward the the red, right? The electrons that are moving toward us do the same, but the spectrum is shifted toward the blue. And finally, the electrons that are moving perpendicularly to us are not going to do anything. There won't be Doppler shift, and the spectrum is just going to stay where it was. This is going to change with the spectral lines very soon when we start talking about Lyman alpha. So now when I average over all these things, what I should do is I should add all these spectra, and actually not just these three, many spectra from many electrons moving in many directions with many different velocities. What I'm going to get is this spectral line, which is broadened by a factor of much, and it's actually very shallow and very broad, and all the spectral lines are going to mix up, and I'm not going to see any spectral lines in the electron scattering in the corona. And this might sound like a very oh wow, why are you telling this to us? This is just a peculiarity, but this is one of the first methods that people use to infer the temperature of the solar corona. Apparently, this Grotrian person was actually a solar physicist, because you find him every so often in the solar physics papers, and he actually used this effect to estimate what kind of velocities we would need in order to have the spectral lines completely disappear in the K corona. And he found that it has to be millions of kelvins, and he said, well, yeah, the temperature of corona has to be millions of kelvins. There we go. Pretty neat, right? Okay. But now comes another question, which will lead us to some very complicated physics, which is the following. If scattering on dust produces absorption spectrum because absorption spectrum is incident, if scattering of electrons produces flat spectrum because, again, incident absorption spectrum is smeared due to the electron velocities, why does spectral line scattering produce emission lines even though incoming spectrum is absorption spectrum? I'm going to give you some time to think, maybe not 3 minutes because we're running away, but I would like to hear some ideas. So we saw that dust scatters whatever it receives absorption profile, it emits, it scatters absorption profile, we see absorption lines, all good. Electrons would like to do the same, but they're moving so fast that it all gets a little bit fuzzy in wavelength, so it's fine. How come that spectral line scattering that we studied in the context of prominences produces emission lines? And we saw that these are emission lines. We saw, example, Hazel inversions. We saw example Hazel spectra in our hands-on. How come that in spectral line scattering, it's emission line? Any ideas? Now we need to go back to the level populations. When we started the lecture, we said that the population of the upper level depends on the incoming radiation. Right. I'm going to show you some equations now, and we're going to go through these. If somebody has an idea, you can type it out, but I'm going to start moving slowly towards this. It's really not obvious, but it's really important. So for the it's not stimulated emission, Michael. Even without stimulated emission, it would be emission line. So let's forget about what lower equation tells us. It's going to be very complicated. Let's just remember that the emission in the spectral line depends on the population of the upper level, whatever it is, times bunch of constant, times this line profile. And this line profile is actually what determines that your line is emission line, because this line profile is simply naturally large in the center of the line and quickly falls off. And then I have a bunch of wavelength independent quantities. So if I'm in the optically thin case, if I don't have anything to absorb my light, I'm always going to get the emission line when I integrate this over length. Does that make sense? There are some confused faces in the crowd. So again, I have emissivity that depends on the population of the upper level. Population of the upper level has no wavelength information on its own whatsoever. These are just a bunch of constants which also don't have wavelength information. This lambda is actually lambda naught, so it's constant. And finally, there is the emission profile. I called it psi on purpose, but don't worry, it's just the emission profile which says line emits most in the center and then toward the wings less and less. So the emission coefficient follows this psi here. So basically my line is always going to have the shape of this psi, and all these other things are just going to determine how strong the line is. Does that make sense? Okay, we are not super clear on that, but I'm gonna move on. But now the population of the upper level, judging from what we talked before, depends on the number of things that are populating that upper level, which is basically this thing here, the number of absorptions. And the absorption collects all the incoming radiation, right? When I'm calculating this J for the spectral line, this mean intensity, I'm integrating over all angles, but also in principle, something that we didn't emphasize until now, but we have to emphasize now, or we are also collecting over all the frequencies, over all the wavelengths. So whatever is the spectrum coming in from here, whether it's absorption spectrum, whether it's emission spectrum, whether it's flat spectrum, I'm going to integrate it to get one number, J. My line is going to take that one number, plug it here in the population of the upper level, and determine the emissivity. So it doesn't matter what's the shape, at least in first approximation, it doesn't matter what's the shape of my incoming spectrum. It only matters how much radiation I have at the line wavelengths. And the emission spectrum is always going to be an emission line for prominences, loops, for every line scattering, a scenario where my optical depth is small and where I'm just basically integrating emission coefficient over the path. I know that this doesn't sit with you now very well, and you are like, oh man, this is completely confusing and very hard, but we can talk about this more and think about this and have this somewhere in the background. And when you work with these things, maybe it will come back. But the main idea is this: emissivity, the wavelength dependent of the emission is determined by this psi, and nu, and nu is constant. It doesn't depend on the wavelength, and it actually only depends on the total number of photons arriving that the line can absorb. Line doesn't worry whether it's, you know, emission spectrum, absorption spectrum, continuous spectrum, or something else. But we'll see soon very neat effect. Okay. One thing that might, you know, sound super hard, and I'm just putting this here so you hear about it, is that in principle, and I mean, this scenario here is something that we call complete redistribution. What does when you hear somewhere complete redistribution, what does that mean? It means, well, when I'm calculating my spectral line scattering processes, I just integrate all the incoming light. I get this J quantity that has dimension of intensity and doesn't depend on the wavelength. I use it to calculate my population of the upper level, and then my outgoing radiation doesn't care what came in. Actually, it doesn't care about wavelength distribution of the intensity that came in. It just worries about the total amount of that intensity. And we call it complete redistribution. Why? Because the photons are completely redistributed. We collected all the photons that are coming to excite, and we said, well, now you are emitted according to this psi here, and that's it. However, in the most general case, there is something called redistribution function that actually, and here I'm plotting it in, believe it or not, the simplest possible way, which means I'm talking about the outgoing radiation and incoming radiation. I'm not introducing opacity, I'm not introducing emissivity, nothing like that. And this basically just says my scattered radiation in given angle and given wavelength is equal to the integral. This is integral over angles. This is integral over wavelengths of something called redistribution function times my incoming radiation. And this redistribution function basically allows you to account for the correlations between the incoming and outgoing radiation, both in the angle and in the wavelength. And Jonathan, you were asking me about these J00s, J02. J00s and J02 come from this thing here. We split this in angle and the wavelength term, and then we further decompose the direction term in outgoing and ingoing terms and do something separately. We can talk about this more in the office hours and in general on Discord and so on and so on. But anyway, let's talk about an example of a scattering dominated line. And one of the very complicated but also very useful ones is the Lyman alpha. And actually what you see here is that for Lyman alpha, radiation starts dominating above the collisional processes already at 0.01 solar radii. So already for some few tens of thousands of kilometers above the solar disk. And Lyman alpha is generally formed in the solar atmosphere, but you can see it in coronal loops and in the many structures that are living in the solar corona, maybe even in the solar wind. The examples that Steve Kramer used in his talk were from the solar wind. So there is an interesting thing, which is again another consequence of this broadening by the high temperatures, is when you look at the Lyman alpha radiation coming from the disk of the sun, coming from the transition region where that light originally originates, very, very redundant. The shape of the spectral line will look like this white line here. So it's relatively narrow, strong emission line with a self-absorption. This self-absorption is a beautiful radiative transfer non-LT effect. We can discuss it in detail when you want. But then the Lyman alpha scattering in the coronal, let's say, features looks like the red line. It is very simple emission line with the huge width. Why does it have huge width? Well, because of what we were talking before. My electrons, my atoms actually, that are doing the spectral line scattering, they collect incoming radiation and they emit it according to the line emission profile. We know that line emission profile will be very broadened because of the Doppler motions. And then what actually happens is we collect this white illuminating light and we redistribute it according to the red line here. And one interesting effect that I wanted maybe to have you think about more, but I think we're just gonna answer the thing now. It is very interesting now to consider what would happen if we have spectral line scattering, where illumination is a narrow emission line, for example, Lyman alpha, but now my blob is moving up. I'm looking from the side, my blob is moving up, and at first you would say, well, nothing is going to happen because you're looking perpendicularly to the motion. There is no Doppler effect, but there is Doppler effect. There is Doppler effect in the way how the blob sees the radiation. So let's look at this, another bad sketch here. I have a blob here. It's running away from the sun, has huge velocity, let's say a few hundreds of kilometers per second. And I know that the radiation leaving the sun has this strong emission shape. Let's imagine that this is my Lyman alpha, right? However, in the frame of the blob, that radiation is redshifted, okay? And the blob is still absorbing according to its own reference frame. It's absorbing according to this green line here, which means that if the blob is moving, it's going to see much less light that is available to be absorbed than if it was if it was at rest. Does it make any sense? That when we are moving away from this, bright source, because we are somehow missing the emission line, We are now having less light that we can absorb and thus less light that we can actually scatter. Okay, there are some pluses. It's not super obvious, but it's all just a neat thing by the Doppler effect. And one way to think about it is to think about, well, I have some very special sunglasses that only absorb at this gray wavelength here. Oh, wow, how neat. This gray wavelength is exactly the wavelength that corresponds to Lyman alpha. If I'm at rest with respect to the sun, I see exactly Lyman alpha. I see a lot of radiation. Everything is cool. Well, maybe it's not everything cool because my eyes hurt, but okay. But now I start moving with a huge velocity away from the sun. What happens? Doppler effect comes into play. The radiation that comes to me is redshifted, but my glasses, they still work in my reference system. So when I look, I'm going to get only these little amount of photons that got shifted to my glass wavelengths, and I'm going to miss the most of the emission line. One beautiful example of this is something completely unrelated to solar physics, but also to solar system, is the people observing quasars at huge redshifts. When they observe quasars at huge redshifts and they want to look at Lyman alpha, do they make filter which works at 121 nanometers? No, they make filters which work at 121 nanometers times 1 plus the redshift of the quasar. And they actually, there is a beautiful paper in which they designed specifically, very specifically for studying one specific quasar, a narrowband filter tuned to the redshift of that one specific quasar. They hooked it up to Keck, 10-meter telescope in Hawaii, observed, boom, Nature paper. Okay, very good. So Doppler dimming, this effect that we just talked about is called Doppler dimming, that when I have redshift, I have less light that I can scatter. I have less emission in my spectral line due to that. And here is a plot that illustrates that. It actually shows you how by increasing the speed of your blob, in this case, it's like a solar wind, you have less and less radiation in the spectral line. So in principle, you can use it to diagnose the velocities that are perpendicular to you. So these are not anymore velocities in the line of sight. These are the velocities that are perpendicular to you. And here are some of the actual observations from, this was a rocket flight that was observing Lyman alpha. Usually Lyman alpha is observed from rocket missions. You might have read the CLASP and things like that. It was, I don't know, this is Lyman alpha 2, maybe this is something else, but you can use it in principle to diagnose velocities. And in principle, there you can also get Doppler brightening, which is, okay, yeah, maybe now my line escaped from my absorption profile, but maybe another stronger line entered there. So now I have even more light than I would otherwise have. Or maybe I was illuminated by an absorption line. So by getting the redshift, now I'm getting the more light than I otherwise would. Okay, we should be finishing now. I'm just going to give you a few slides on the forbidden lines. Forbidden lines are not literally forbidden, otherwise we wouldn't really see them, but these are lines that would be generally unobservable in photospheric or chromospheric or even laboratory conditions. But you can see them sometimes during the eclipse, and these are actually forbidden lines. So here you see a very nice emission spectrum during the solar eclipse, and some of the lines you are very familiar with, like for example H alpha, helium D3, H beta, H gamma, and we know that these are lines that can be seen above the solar disk simply because these are very abundant elements, and we can get some scattering there, even though these elements are mostly ionized. But we also see these lines of iron 10 and iron 14, which in principle shouldn't exist. And you only see them in the coronal spectrum. And these are the famous red and green forbidden line of iron. How do forbidden lines, and what are the forbidden lines? Well, forbidden lines are the lines which have very low Einstein coefficient of spontaneous emission. This should be small s here. I really don't know why I used capital. This is 10 to the 1 to 10 to the 3 per second. If you think about back, you might remember that I said that Einstein coefficients go from 10 to the 5, 10 to the 6, even 10 to the 8 per second. And these are many orders of magnitude less. Well, what does this mean? Well, it means that when I go to my statistical equilibrium equation my AUL is simply so low that I can't neglect collisional de-excitation anymore. So regardless of what my excitation thing is, we're going to assume most of the time that we're going back now basically to the case of the collisional lines from the last class, where we were neglecting BLU and BULJ, but we can't neglect NU-CUL anymore because collisions are becoming important for de-excitation. And now if I want to find my NU, I have to actually write a little bit more complicated expression. And here I broke CUL and CLU into electron density times some constant that actually depends on the temperature. It's not really a constant. It's something like a cross section for collisions. And if I'm looking for my magical quantity that determines my my dependence, my emission in the line, it's going to look something like this. I have NL coming from here, then NE omega LU coming from here, divided by AUL, NE omega UL coming from CUL. And now let's think about this. Well, if my line wasn't forbidden, my AUL would be much larger here. I could scratch this and I could just move AUL to the left. Everything would be good. But it's not. These two terms are of similar quantity, which will lead to a very awkward situation. It will lead to the fact that my dependence of my emission coefficient is not quadratically dependent on the electrons, on the electron density, as we had in the last class, but is dependent something between linearly and quadratically. It behaves as NE to some degree, which is between 1 and 2, and that 1 and 2 depends on what's the ratio between these two quantities here. Right? It actually changes on the electron density itself. Okay. I just want to stress that if you had too much material, your AUL would completely drop out. But then again, if you had too much material, you would basically retrieve back the Planck function and you would get no spectral line whatsoever, right? And actually for forbidden lines, it happens very, very easily that you don't see them. So what we can do with these forbidden lines? Well, since their dependence on the electron density is so peculiar, we can actually use them to, we can use pairs of forbidden lines which have different density sensitivities, which have slightly different constants here, playing the roles here. We can use them to diagnose the electron densities. And here is an interesting plot using two spectral lines of, I think this is iron 14. So these are still ultraviolet, far ultraviolet lines, 35 nanometers. So we have two forbidden lines of iron here, and we can see that, the ratio between lines depends strongly on the electron density. And we can observe these two lines, measure their ratio, and just read off the electron density, and voila, and this is actually much better electron density diagnostics than what we talked about last time. And there is one more slide which I definitely suggest you have a look on your own. I want to show it already for the second time. I didn't have the time to do that, but these are observations of calcium 8542 in coronal loops where it shouldn't be, but apparently there is some. And by doing that, these people measured magnetic fields and found very, very strong magnetic fields. This is, I'm just going to finish here. I'm not going to go further. This is everything that we had for today. And that's everything that we had for the Corona. We are done with the lectures for our course. Next time on Thursday, I'm going to show you an example of multi-height inversions. So we're going to look at inversions of helium-10A30 and nearby silicon line to see how we can simultaneously capture the physical processes at various layers of the solar atmosphere. Sadly, there is no corona, but there is photosphere and chromosphere basically together. And we will really look at the performed inversions and plot temperature maps, velocity maps, magnetic field maps, look at the spectra, and so on and so on. We will do that for some 45 minutes. And after that, we'll just talk about the course and what you would like to see in the upcoming years and in general. So this is where we finish, and I'm stopping the recording, and I'm open for all of your questions, critiques, suggestions, and etc. Oh no, I wasn't supposed to stop. I mean, I can also stop sharing, but I was supposed to stop recording.